so we got these equations of motion that get rid of our nonlinearities and allow us to come up with analytical solutions. That's super awesome. What we're going to do next is we're going to actually take these and get an analytical solution. In essence, we're going to solve these differential equations. However, before doing so, I want to talk about the process or the philosophy of solving differential equations. And in particular, I'm going to liken this process to the process of constructing or erecting a building. Now, what happens when you put up a building? When you put up a building, the first thing you do is you usually put up some kind of scaffolding or support structure. And once that is in place, you sort of know what the building is going to look like, right? You know the general shape, you know how tall it's going to be. However, the minute details are not filled in, right? Once that scaffold is up, maybe you put up the buildings, make it look nice, put some kind of design on it. You put in the piping system, maybe the electrical stuff, air conditioning. Maybe on the outside you put on windows, you have a garden, and so on and so forth. So once you have this general outline of what the building could be, or in other words, a support system or your scaffolding system, you know what it generally looks like. The entire process of constructing a building consists of filling in the minute details. Well, guess what? Solving differential equations is no different. What happens is you take a schematic, which is similar to, maybe blueprints for a building, which gives you a general idea of what it's going to look like, but you have to spend time taking that idea and making it tangible in reality when you build a building. With differential equations, you say, okay, I'm going to assume some kind of scaffolding system, how it's going to look, and then I'm going to use a schematic of information I have, or equations of motion that describe how the system should behave, or the final product, what it should look like, and I'm going to fill in the little details, okay? The way in which this happens is we say, based upon our physical intuition, based upon how we would expect the system to evolve, I'm going to assume a solution of some form. I'm going to put up a scaffolding system of the general shape and outline of this building or this equation or solution. And, it might have some constants, some undefined variables. And then what I'm going to do is I'm going to take my schematics, the information I have, equation of motion, and my initial conditions, and I'm going to define my assumed solution more. I'm going to define the constants such that I get a finished product, a finished solution. That's what we do when we solve differential equations. So for example, we might assume, maybe it's an exponential term. Maybe y sub x equals e to the x. But, there are a ton of functions that can behave like this. So I need to define it a bit further. I'm going to put a constant in there. I'm going to fill in the details of this using my equation of motion or my initial conditions. Okay? That's the approach we're going to take here. How are we going to do that? First, you need to understand how synchronous or vibrational systems operate. Now, if you have a synchronous system, dynamical system, which, it vibrates back and forth, which is the case here, we have a pendulum that's going. It's a synchronous system. So we would expect that there are solutions in which we have normal modes. Now you hear that word. Maybe you've heard it before, maybe you haven't, but this is a mathematical term, sort of unintuitive. What does this mean? It basically means that, when a synchronous or vibrational system evolves, every point along that system is going to have solutions such that every point vibrates at the same frequency, but perhaps at a different amplitude. I'm going to say that again. That's very important. A normal mode is a solution for a dynamical system in which every point along the system moves at the same frequency, but perhaps a different amplitude. Beautiful stuff. What that means is that if we think of it in terms of our system, it's going to be moving back and forth, if we think about simple harmonic motion, there's one normal mode, right? All the particles are moving with the same frequency, or perhaps a different amplitude. In this case, the amplitude is the same. If we look at our problem, we can have two different normal modes, if you think about it, from a physical standpoint. We can have an instant in which the two bobs are moving asynchronously and synchronously. For example, you may have something like this. They're moving with the same frequency, perhaps different amplitudes, but they're going back and forth at the same rate, right? That seems plausible, right? You could have that scenario, or you could have something in which they move in the same synchronous manner, right? They could go back and forth. Two different normal modes. And we know from the principle of superposition that the general solution is going to be a linear combination of those two solutions, or a combination of the normal modes. This makes sense from a physical standpoint because you can think of a guitar string, for example. When you hear the sound from a guitar string, you have different normal modes in there that are built up, right? You may have different octaves that are included together. In essence, you have different frequencies, different normal modes, different solutions that give you certain noise. And when you put them together, you get a full nice noise. It's sort of like a chord in guitars. You have all these individual notes, but together you get the full thing. That's how the generalized solution is going to work. It's going to be a linear combination of our normal modes, of solutions in which every point along the system moves at the same frequency, but perhaps a different amplitude. So for that reason, what we're going to say is that we're going to assume a solution, we're going to put up a scaffolding system of what we expect the solution to be, and then we're going to fill in the remaining details. We're going to define the constants and try to take our generalized solution such that it applies to the problem at hand, right? So we're going to say that we're going to assume that the solutions, or the normal modes, just a fancy term for what we were just talking about, it's just a solution to a synchronous problem. We're going to assume that the normal modes are of the form as follows. We're going to have theta 1 sub t, and we're going to have theta 2 sub t. Now, if this is a synchronous problem that goes back and forth, what kind of function does that make you think of? If you think of cosines and sines, trigonometric functions, right? And furthermore, we've seen this already, right? We've seen with the simplified harmonic motion, very simple problem, that we get a cosine. So we'd expect to have similar solutions. So, intuitively, it makes sense to guess a solution of that form. So if we have cosines and sines, we can use the Euler identity, say that it's going to look like e to the I omega t. That's the frequency. We know it's going to operate at some kind of frequency. And to fully define this, we're going to have a constant in front. That we're going to have to define using our equation of motion or our initial conditions, okay? So what do we do for theta 2? Well, we know that normal modes give us solutions such that every point moves at the same frequency. So this guy is going to have that. Right? It's going to have the same frequency. And furthermore, based upon our discussion, we'd expect omega to have two solutions, two natural frequencies. Again, that's just a special term for the frequency associated with a given normal mode, a natural frequency. So what we're going to say is this is our scaffold. This is what we want to build for us. This is the solution we want. We want to see if it's applicable to the problem at hand. Is this a valid solution? So we plug it in here and try to fill in the details. We're going to try to figure out what theta 2 naught, theta 1 naught, and omega have to be in order to conform and satisfy these equations of motion. We're taking a general assumed solution and conforming to what would happen in nature. We're basically trying to mold it and sculpt it such that it conforms to what we expect it to do, such that it conforms to the information we have. The problem we're looking at has to satisfy this. So we're going to ensure that this satisfies this. Okay? That's the general approach here. So what we're going to do is we're going to plug these guys into this and see what happens. Okay? So I'm going to call this 1 and this 2, just to be a bit more organized. So if we plug into 1, what's going to happen is we see theta 1 double dot. Okay. We want to take the second derivative of this. So that's going to be I squared omega squared theta 1 naught e to the I omega t. Right? Do you guys see that? Because the derivative of this is the exponential itself, and then we have the chain rule, I omega. Do that 2 times, we get I squared omega. Now, I is equal to the square root of -1. I squared is simply that. So what we can do is we can take this guy, get rid of that, put in a negative term there, and that is going to equal negative g over L 2. We're going to plug in theta 1 naught e to the I omega t minus theta 2 naught e to the I omega 2 omega t, and we need to simplify. What we can do is we can get rid of the exponential terms, right? So our only unknowns here are the omegas and our constants. Did we gain anything here? Seems like we didn't. Well, let's keep chugging along and see what happens. So we also want to plug into the second equation of motion, right? When we do that, theta 2 double dot, take the second derivative of this, same thing happens. We get I squared omega squared theta 2 naught e to the I omega t. Now, again, it's the second derivative. So the derivative of the exponential, this is just a constant. Derivative of this is going to give us e to the I omega t times I omega t. Chain rule, baby. Then, second derivative is going to give I squared omega squared e to the I omega t. Again, this guy is -1, so we can erase that. A negative in there. And that is going to be equal to 2 g over L theta 1, which is theta 1 naught e to the I omega t minus theta 2 naught e to the I omega t. All right? Again, this is a common term, the exponential. We're going to cancel this guy out. So, you're probably thinking, we didn't get anywhere with this. What are you doing, man? What the hell are you doing, bro? Well, let's take this and sort of use our linear algebra skills and see what happens.